Lesson 9 looks at matched pairs. So in the previous lesson, we compared averages for two independent groups. We did this using the model x bar 1 minus x bar 2, had a student t distribution. We took the smaller of the two degrees of freedom. We subtracted the averages, and we looked at a big square root that contained both of those standard deviations combined into one there. Today we're going to consider situations where they're not independent, and in fact there's something that links them together. So for example, these are the same people with their starting weights and ending weights for P90X. And this first page is just going to analyze this group of people, single group of people, to see what's going on. So first thing I want to know, how much did each person lose? Well, to figure out how much they've lost, and let's use the letter D for difference here, I'm going to take their starting weight, and I can subtract from that their ending weight. So in this case, I could do 185, take away the 165, so Sam's difference is 20 pounds. And contrast, Carol went from 190 to 172, that's 18. One thing I have to be a little bit careful about is signs. So notice this is a positive for difference when I do the start minus the end. Sam went from 185 down to 165. So whenever I have a difference that's bigger than 0, this represents weight loss. Now looking through the table, it might not be the case that everyone has lost weight. In the situation where I have a difference that's less than 0, this will tell me that the person actually gained weight. This is remarkably similar to the comparisons we were doing last time when we were looking at the signs positive, negative, or 0. Should someone have a difference of 0, this tells me that the starting weight would be exactly the same as the ending weight. In other words, neither a weight loss nor a weight gain. So the signs positive, negative, or 0 for each of these people will be telling me what's going on with their success using this P90X program, assuming they're using it here for weight loss instead of like adding muscle or anything like that. Enrique went from 170 to 160. That's a loss, should be positive. 170 minus 160 tells me Enrique lost 10 pounds. Rebecca went from 160 to 158. She lost 2 pounds. Eric went from 240 to 242. So if I do this subtraction, I end up getting a -2. He did not lose weight. Eric was the only person in this group that actually gained some weight. And it might be the case that on average people are losing a fair amount of pounds, or it might be the case that they're gaining pounds. So let's try to figure out what's happening on average per person. So I'm going to find an average for those differences. And I'm just going to pretty much ignore the starting weight and ending weight because I don't really care where they started or ended. I just kind of am concerned about what was their difference from the start to the beginning. For Sam, it was 20. For Carol, it was 18. And I'm adding all of these things up. I'm just finding an average like normal. One, two, three, four, 5 individuals. When I type this into a calculator, I get 9.6 units are pounds. On average, people lost 9.6 pounds. Pretty good. Now, not everyone lost weight. We saw Eric gained weight. So let's see what's going on with the spread for the data. Before I can find the standard deviation, I'm going to find the variance first. To find the variance, I take the first value in the table, 20, minus the average, 9.6, squared. Next value in the list is 18, minus the center squared, and I'm going to add all of these up, and then I'm going to do 10 minus 9.6 squared, 2 minus 9.6 squared, -2 minus 9.6 squared. And I'm going to divide this by the number of terms, 5, take away 1. This denominator of 4, this n minus 1 thing should look a little bit familiar. This is actually the degrees of freedom that we're working with when we're doing these t distributions. Now I'm going to type this into my calculator and I'm going to see what I get. I get a massive number for the variance of something like 92.74 or so. If I want the standard deviation for these differences, standard deviation, I might even use a subscript of d to remind myself that I'm not concerned about starting or ending weight. I'm really just concerned about what the difference was for their weights. So the standard deviation is the square root of the variance. Square root of that 92.74 number is giving me approximately a standard deviation of something like 9.63 pounds. So the big question is, well, why can't I just use just the starting weights and ending weights independently? Why do I have to consider these as sort of a matched set where I find the differences first? And the reason for this is I'm looking at the same person when I'm doing the before and the after. The data is linked. Whenever there's a linked thing going on, I should work to find a difference of the two columns first before doing anything with the data. The reason for this is the before weight affects the after weight. So for example, it's going to be really unlikely that someone goes from 120 pounds to 300 pounds, but if someone started at 350, they could conceivably end up at 300. That's a bit more realistic. So whatever weight they start at, in some sense, that's predicting what their ending weight will look like. There's a relationship between the variables. So 9.6 pounds on average, standard deviation of 9.63. Let's try to figure out with 90 or 95% confident what the average weight loss is for people overall, kind of using this sample of 5 to extrapolate what's going on for the larger population. And it looks like I'm working with a single set of information. So when I tried to create this 90% confidence interval for the before and after, my average is 9.6 pounds. My standard deviation was 9.63 pounds. And I'm going to use the letter K. K is equal to the number of people. And my K for this problem was 5. I was looking at 5 people. My degree of freedom, if I'm looking at 5 people, take away 1, I have a degree of freedom of 4. That degree of freedom showed up in this variance calculation from earlier as well. That's not the first time 4 has shown up in this problem. Now, when I'm looking at this, I don't see the before or after. I only see a single average that I'm working with. So my thought is I'm going to take my formula for a confidence interval for just one group. And I'm going to plug in the values and I'm going to see what I get. The average was 9.6. If I go to my table and I see the spot where the 4 lines up with the 90, I should get my T star. Let's find that T star here. So I'm in the 4 row meets the 90. I have 2.132 sitting there. My standard deviation S here, this was the number 9.63, square root of my number of samples that I was dealing with were 5 individuals. I'm going to type this into my calculator, once with a plus and once with a minus. When I do this with the minus on the low end, I end up getting 0.418 pounds. And on the high end, I end up getting 18.782 pounds. Now, this doesn't mean that someone weighed 18 pounds. That wouldn't even make sense there. This is telling me how much weight they lost on average. So my sentence that would go along with this is we are 90% confident that the difference, the average weight loss, was between 0.418 pounds to 18.782 pounds. So the follow-up question is, how do we know if the program was actually effective at weight loss? And has it been effective? Well, let's go back to the science. So reminder, if we have a positive number for the difference, that told me they were losing weight. If they had a negative number, that told me they were gaining. This was a positive number. It's bigger than 0. This was also a positive number. That's greater than 0 as well. So my confidence interval for the difference being that starting weight minus the ending weight, ended up being greater than 0. Moving this n to the other side, this tells me that I have evidence that the starting weight was higher than the ending weight. In other words, if my average for the differences is bigger than 0, like it is here, I'm experiencing weight loss. If the average for the differences is less than 0, that's an example of a weight gain. And finally, the only other situation that could happen, if the average of all of the differences was equal to 0, this is no change in the average weight. So here's something that I find interesting. We were able to create this confidence interval, and we didn't even have to come up with a new model. We're just using the same model that we were previously using when I'm looking at differences. So at the top of the page, I have a spot here where I go over the similarities between the model. Let's take a look and see what's going on. So this is an example of matched pair data. The start and the end are linked together by the person. There's usually some sort of before and after dependency that keeps me into that. So instead of looking at the before, instead of looking at the after, we analyze only using the difference. And the difference is the before minus the after. So when I was looking at the grid of information, I didn't have two lists of information. I can truly condense this down to just one list, one variable that I was concerned about. So my confidence interval, I'm going to still have this be based off of samples, but I'm going to take my center plus or minus t star, my standard deviation over the square root of the number of samples. Now I'm going to give this slightly different notation for where these numbers are really coming from. When I say average, I mean average of the differences, so that was my d bar. When I was talking about standard deviation, it was standard deviation for the differences. And instead of calling it n, or if I'm talking about n, that might be the size of either one of these lists, I truly am curious how many people are there. K equals 5 was the number of individuals. So I'm going to divide by square root of k, where k is the number of groups. So my confidence interval formula, exactly the same thing as before. So if you're wondering, do I have to memorize something new? Not at all. You're just using the same formula that you've been using before. It happens to have different notation, but if you just plugged in the numbers like normal, everything would work out just fine. Likewise, when I'm doing my hypothesis test, I'm going to have this set up using the same model I had before when I was looking at a single average at a time. Confidence intervals will always be based off of samples. We just did one of those. Hypothesis tests are always going to be based off of claims. And in particular, my null hypothesis is always going to represent there being no difference in the groups. So when I'm dealing with matched pair, my null hypothesis is always going to be equals 0, meaning I cannot tell the difference between the two groups. Your alternative hypothesis when you're doing matched pair, it's either going to be less, greater, or not equal to 0, depending on if I'm testing for a weight loss, a weight gain, or just a change in weight. We just looked at this P90X data for a confidence interval. Let's try to do the same thing now with a hypothesis test and then put everything together. So same thing that I just had on this last page, I'm bringing it back again. What would it mean if the average was greater than 0? Well, this would tell me that the starting minus the ending would be greater than 0. That's the same thing as saying the start weight is larger than the ending weight, and that means you've lost weight. If the average is less than 0, so this is the same sort of comparison I was doing for two proportions and also for two independent averages. The only difference here is I'm using essentially one list to test the relationship between two variables. If the starting weight is smaller than the ending weight, then they've gained weight by the end of the program. And finally, if I have the average difference is equal to 0, that's telling me the starting weight looks like the ending weight. In other words, there appears to be no discernible change in their overall weights. Knowing this, let's do the 4-step process to determine if people on average lost weight using the P90X program. It's a hypothesis test, so I'm going to have the same 4 steps that I always have. Hypotheses, my model. I'm going to calculate my p-value, and then I'm going to state my conclusion. I'm not really concerned about their starting weight or their ending weight. I'm only concerned about one variable in this problem, and that is their difference in weight. Null hypothesis represents there being no change. So for my null hypothesis, I'm going to have equals 0. That means they have not changed their weight. Units, pounds. Alternative hypothesis, I think on average, they've lost more than 0 pounds. Model. Well, my model is X bar is a t distribution, mu is my center, S over the square root of n is my standard deviation. Now, I'm just going to write this with our new notation, even though it's the same thing. Looking at averages on difference, a t distribution, my average or my center always comes from the null hypothesis. This is going to be 0, representing no difference. I'm going to take the standard deviation for the difference in weights over the number of people. K represents the number of groups or the number of people. So plugging in my information from before, this is a t distribution, my degrees of freedom. I had 5 people, so I have 4 here for my degrees of freedom. 0, comma, my standard deviation for the P90X information was 9.63. My standard and my n for finding the standard deviation was 5. I'm typing this into my calculator. When I do so, I get an average of 0 and a standard deviation of about 4.307. So if I draw my picture, my center is 0, and I'm roughly counting by about 4.3 pounds. This entire side of the curve here, this represents a weight gain. This entire part of the curve, this represents a weight loss. The center represents no change in weight. So the curve really represents everything that could possibly happen for my sample. And the p-value is the likelihood of my sample data, in this case, my D bar. They lost 9.6 pounds on average. The likelihood of my sample data or more extreme, I'm wondering what's the likelihood that they lose 9.6 pounds or more than that if the null hypothesis is true. So I'm going to put this 9.6 on the curve. I'm going to shade out, and the p-value is going to be the likelihood of the sample data or more extreme. It's going to be the size of this little tail here. So ultimately, this thing is going to start at some t-score. I don't know what that is yet. I'm going to leave myself a little space for that first t-score. And it's going to keep going on to infinity. This is a right-tailed test. And I have degrees of freedom of 4. Degrees of freedom of 4 because I had 5 people, and 5 take away 1 gives me 4. I need to find that t-score, or my test statistic. I find t by taking my value, 9.6, minus the center, 0, and I divide this by my standard deviation, 4.307. When I type this into my calculator, and even looks like it's a little bit more than 2 tick marks away, I get 2.23. In your calculator, go ahead and do TCDF 2.23, comma infinity, comma 4. Pause the video and see what you get, and then see if you could come up with a conclusion. I will give you a second to do so. If you're joining after pausing that video, let's see what we get. When I type this into my calculator, I got 0.045 or so. This is a small p-value compared to something like 5%. So for the conclusion, my p-value is less than an alpha of 5%. If my p-value is low, the null must go, so I would reject the null hypothesis. If I'm rejecting the null hypothesis, I have evidence of something. I have evidence of the alternative. In this case, the alternative was this greater than 0. I had evidence that people lost weight on average with this P90X program. If I want to know how much they lost on average, that's what my confidence interval tells me. So anywhere from 0.418 of a pound all the way up to 18.782 pounds. This was a confidence interval we had on the previous page, but my results are matching up. I have evidence that they have lost weight. Confidence interval tells me how much weight I think they've been losing on average. Now, all of this stuff still follows the same vocab as before. So in this situation, if I made an error, and it's possible that I make an error because I have a really small sample size, probably too small of a sample size to actually do any of this analysis, then I could have rejected the null hypothesis when the null hypothesis is true. That would be a bad thing, to throw away the null hypothesis when I wanted to actually keep that thing if it was true. If the first thing was true and I make a mistake, this sounds to me like I could have potentially made a type 1 error. I'm not guaranteed that I made an error, which is good, because if I was guaranteed to make an error, I'd never do any tests whatsoever. I would just screw everything up, and there's no point in doing it if I just continually screw everything up every single time. But if I were to make a mistake, my likelihood of making a mistake with processes like this, I'm willing to be wrong 5% of the time. That would be a type 1 error. And that's all there is to this. I'm not really doing a new lesson per se here, as much as I'm just taking these old formulas and I'm using them in slightly new situations. So I've got a really data-heavy problem that I would encourage you to go through. And this is looking at starting and ending times for the mile for 12 runners at a high school to see if they've been effectively trained. I strongly, strongly recommend doing this on your own just to see what kind of results you end up getting. You can always email me and I'm happy to help you out with questions like these, but try this one and see what you get. Okay, to me the math isn't that bad for this. In fact, I think the math is easier for matched pair than it is for two independent means, but the hardest part by far for me is trying to figure out which formula I'm supposed to use in which situation. So I'd like to spend the remainder of this video kind of looking at that aspect more than doing another one of these problems that's identical to the P90X thing. So I have two different models that I could be using. If I am comparing two independent averages, then I am using the longer formula. If I have data that's matched together, some sort of before and after thing, then the model I'm using there is really just my one average model. So I'm going to take a look at example 9 where I'm seeing a whole bunch of different scenarios, and I'm just going to try to figure out, is this matched pair or is this two independent? And in each of these scenarios, I'm also going to see if I can figure out what the degree of freedom is, or at least what a reasonable estimate should be for that degree of freedom. I'm going to read through each of these problems, and then I'm going to suggest that you pause the video after I read through it and see what you are thinking. So for part A, we want to compare the age gap between two people in a relationship, and we study 60 people. That's the same thing as 30 couples. So the question here is really, do you think the age of one person affects the age of another person in a partnership, or do you think there's no relationship for age for people in relationships? So go ahead and pause the video and let's see what you can come up with. Okay, when I look at this, I'm thinking if I see a person in a relationship and I know that they're, say, 18 or so, I would expect their partner is probably going to be more likely around the age of 18 than, say, 81. I imagine people are relatively going to be close together in age. Not always. You're going to have some people that are in their 30s that are dating people in their 70s, but for the most part, the age of one person predicts the age of another. It is linked data. And because it's linked, I would say this is matched data. So I'm not really looking at the number of people as much as I'm concerned about the number of couples, my before and my after. If I have 30 couples, my degree of freedom here is going to be 29. Let's look at another example and see what we can come up with. We want to compare the average time it takes to get to work using two different routes. So randomly select 60 days. I do 30 on one route, 30 days on a different route, and I'm not doing the same day, 2 different routes. So I'm doing one or the other, never both. So go ahead and pause the video and see what you could come up with for the model. So for me, there's no relationship that links these things together. It's not the same day. So it's not like road construction is going to affect both of these things. It's not like there's going to be icy roads on the same day that's linking them together. Since there's no relationship, I would say this is 2 independent means. And if it's 2 independent means, I'm going to base the degree of freedom off of the smaller of the 2 groups. Well, they're both 30, so the smaller group has a degree of freedom of 29. Now, unlike the last one where it's exactly 29, this is actually approximately 29 because this is using that in-class lie estimate that gave us really, really close results for our confidence intervals and hypothesis test, although the degrees of freedom would be different if you used your calculator. C, we want to compare the number of credits taken by Sylvania and Rock Creek students. We sample 70 Rock Creek students and 80 Sylvania students. I know something right off the bat on this thing. I noticed that these 2 things have different sample sizes. So there's no way I can match these things up perfectly if I have more samples in one group than the other. For this reason, I have 2 independent means. I can't match them. A student at Rock Creek is not affecting a student in Sylvania if they're totally unrelated. I'm basing it off of the smaller degree of freedom. The smaller group here is the 70. So I have about 69 for my degree of freedom for this problem. Next one. I want to measure how long it takes to complete a crossword with and without coffee. We measure the amount of time it takes 20 people without coffee, and then remeasure the same 20 people with coffee. For me, I'm seeing this before and after, with coffee and without coffee. And it's linked for the same people there. And because it's linked, I'm hearing matched pair. If it's matched pair, it's not based off of the 40 people in total here. It's really just the same 20 people, right? Same 20 people at the start and at the end. So my degree of freedom would be exactly 19. It is based off of the number of groups. Finally, we want to compare, oh shoot, I think I might have a typo here. Can you pause the video and read E for me? I feel like I might have had a typo here. And if I do, I'm so sorry about that. But read through and see what you get for your model and your degree of freedom. Let's take a look. I'm sorry if this is an error here, but I'm just going to do my best and read through. We want to compare how long it takes with and without coffee. We measure the amount of time for 20 people without coffee, and then 20, oh shoot. One word has changed everything here. I'm not looking at the same people. I'm now looking at 20 different people. So previously where I had the same people before and after linking it together, I now have 2 distinct groups. So this has become, instead of matched pair, 2 independent means. Same variables, I'm looking at the same relationship here. I end up with a really similar degree of freedom, but it's a totally different model. And in this way, it's often possible to set up the same sort of experiment using different scenarios, whether that be matched pair or 2 independent. And often the trick is the word same is telling me that it's matched. And if I'm splitting it up amongst different groups, that's when it starts to become independent. So for example, to design a matched pair study that would analyze the effects of new medication on balance, well, I would probably have people before taking the medicine and their balance time after taking medicine. And I would do this for the same people before and after. In contrast, if I wanted to set this up as 2 independent means, I could have a without medication and a totally separate group with medication, and then I can compare these two separate groups. So matched pair, I'm looking at same people. Two independent, I'm often looking at different people. Which of the previous two study designs do you prefer? Which one seems more practical? Well, for me, I think that I prefer the matched pair, because maybe there's something about the balance of the person to begin with. They might just be really, really good at balancing, and I would want to know more about what the difference in their balance was instead of looking at their individual value. So for example, if one person could balance for 27 hours and everyone else could only balance for 5 minutes, that 27 hours would be an outlier for both of these groups, and it would completely screw up my result for both of those values. But if it was matched and I looked at the difference between 27 hours and 27 hours, that difference gets nullified down to 0. So I'm really testing the true difference when I'm dealing things with matched pair. In general, matched pair helps to eliminate potential bias. Now the downside is matched pair takes a little bit more time, because I can start collecting balance data for two different groups almost immediately without having to track the same people. It is less work for me to do two independent. I often get better results with matched. There's no best way to do it. One thing might be more accurate, but more accurate taking more time is not always the best thing. Again, my models for this, my matched pair model, this is my D bar, has a t distribution, mu s over the square root of the number of groups. My two independent looks like two separate models that have been shoved together. It is. Where matched pair looks like one thing that's been melded together into a single model. It also is. Perform the indicated inference. Diane wants to compare the final exam averages for students in Math 243 that have come from 95 and from 111. So she randomly collects the data here, and she ends up getting the average grade for 95 students, for 111 students, and she is looking also at the difference from 111 and 95. Test if students coming from Math 111 do better in 243 on average. If so, how much better? So let's try to figure out if this is matched pair or if this is two independent before I try to do any of the math. And the thing I'm trying to figure out is, am I looking at same or am I looking at different? I'd like you to pause the video and see if you can figure out, is this matched pair or is this two independent? When I looked at this, I noticed that there was 40 students coming from two different unrelated classes. So they're totally separate groups. So this is two independent means. As a result of that, I'm going to be looking at each of the unique pieces of information for those two groups. It would have been inappropriate for me to try to subtract those values. There's nothing that links them together. This says test. It would probably be better to do a hypothesis test. I'm just going to create a confidence interval for the difference in Math 111 minus Math 95. And I'm going to create a 90% confidence interval here. Just as a note, do the test as well to really see what's going on. So I'm only answering half of this question. test if there's a difference. If so, determine how much. I'm doing the latter part. I'm determining how much. I'm looking at two independent means. So my formula here is going to be average of the first group minus average of the second group plus or minus my t-score for, and I have a degree of freedom of 39 square root first standard deviation over n, second standard deviation squared over n. And I'm going to plug in some numbers. Average for 111 was 85%. Average for 95 was 72. Degree of freedom, so I'm looking at 39 for my DF. I'm going to go to the table. 39, I don't have 39, but I have 40. If I wanted to be 90% confident, that's 1.684. First standard deviation squared over the n, 40 people. Second standard deviation squared over n, that n was also 40. This is going to give me a low value and a high value. I'm going to type this into my calculator here real quick and see what I get. So this is just reviewing an old lesson. I'm just trying to tell the difference between them. And when I'm typing this into my calculator, I'm not going crazy with the parentheses. I'm just letting order of operations do its thing. On the low side, I'm getting 8.86%. On the high end, changing this minus to a plus, I'm getting 17.13% or so. I'm noticing that my confidence interval for math 111 minus math 95 is positive. Both these values are greater than 0. If it's greater than 0, I'm going to move that 95 to the other side. This is telling me that I have evidence that math 111 students do better in 243 than math 95 students. If I'm wondering how much better, anywhere from 8.86% better up to 17.13% better. So as soon as I know which model to use, I can plug in those numbers. So let's suppose that someone at the Student Learning Center wants to do something similar where we're looking at success rate. This time though, we're trying to figure out how students spend time in the Learning Center. So let's suppose samples 31 students, fall and winter term, and she samples the same students there. Okay. I'd like you to pause the video and try to figure out what model are we using and what should our degree of freedom be. So I'm looking at the same students. Go ahead and pause the video and see if you can figure out what type of model I should be using. When I hear the word same, I'm hearing matched. In particular, for the difference, I can take the amount of time they spent in the winter term, and I can subtract from that the amount of time they spent in fall. It's a comma thing, fall, comma, winter. It's linked by the person. If there are 31 people, my degree of freedom here is going to end up being that 30. So I don't want the fall information. That's not useful. I don't want the winter information. It's linked together. I only want to use the information for the differences. So when it's two independent means, I need information for two groups. When it's matched pair, I only need information for one group, and that one group is the differences. So in each of these problems, I was given extra information that I can't touch, and that's okay. I'm also going to make a confidence interval here, 90% confidence interval, but this is going to be for the difference when I took the winter value and I subtracted the fall. Again, I would also recommend, just like on the last one, do the test as well, just to make sure that your results are matching up with what I'm getting for the confidence interval. I'm really doing the second part of this problem where I'm determining how much things have changed. I'm looking at a single group. So I have my confidence interval formula for just one group. Degree of freedom is 30. I'm going to plug in my values. The average was a -6. I have to be really careful about the signs when I'm done. That's okay. 90% confident, and I'm looking at 30 as my degree of freedom. I got a t-star of 1.697 for that. Standard deviation was 2.4. Square root, I'm looking at 31 samples. Matched pair has a lot of the same kind of setup as that confidence interval I had above, but I only have to do it once, where for two independent, it's really like I have the same formula repeating twice. I'm going to type this in once with the minus and once with the plus. When I do this with the minus, I end up getting -6.73 units here are hours. When I do this with the plus, and I'm really wondering if I'm going to end up with a negative positive, because whenever I end up with a negative and a positive, that tells me zero's in my interval and the results are inconclusive. So if this is negative, negative, it is, that tells me that there must be some evidence of a difference between the groups. In particular, my confidence interval for winter minus fall, these were negative, they were less than 0. So moving fall to the other side, this told me that people were less likely to use the Learning Center in winter term compared to fall term. If I'm wondering, well, how much less? Anywhere by 5.27 hours less, all the way up to 6.73 hours, and this is with 90% confidence. So I would say I'm 90% confident that students spend less hours in the Learning Center during the winter compared to fall term, anywhere from 5.27 hours to 6.73 hours. The reason why I'm doing confidence intervals for both of these things is it answers the question, is there a difference? But it actually goes one step further and it tells me what that difference is. I think this is a great page to go back to because it reviews essentially everything that we've learned so far about averages. We have one average. One average is the same thing as matched pair. And we have two independent averages. These are our two big models that we're working with when we're dealing with inference involving sample averages. We're going to take a break from averages for a little while, and we're going to compare. Previously, we've looked at one proportion and one average. We've looked at two proportion and two average. I want to see how can I compare like 27 groups at a time. So the next couple of lessons are going to be comparing multiple proportions and counts. That's going to use something called chi-squared. And that's going to get followed up by something that compares multiple averages. And that's going to be done using something called ANOVA, analysis of variation. So those are the next big lessons that are coming up, chi-squared and ANOVA. As always, great doing some math with you here. And I'm always happy to answer questions if you have them.